Let's start. I see. Okay, so last time actually we were trying to show this projector, the projection onto symmetric subspaces. So we were doing that. Let's quickly recall the statement. Excuse me. Okay. So the notation we were using was this. So we were calling this the symmetric projector. D comma k defined as 1 by k factorial sum over permutations, right, and v d pi. Right, that was the definition for the symmetric projector. And the definition was justified because it actually does project onto the symmetric subspace. Right. So PDK is the orthogonal projector, and we had like a little bit of discussion on what orthogonal projector means. I still don't know if I found a fully satisfactory thing, but at least last time we had some notion that we could prove it satisfies. Symmetric subspace. So PDK is the orthogonal projector on the symmetric subspace, which we wrote as SymK CD. Right, that was the definition. Forgot to silence. Okay, so for the proof, we completed a few steps. So we showed that VD pi P symmetric. So I'm just going to write P now. Okay, I'll not write symmetric every time. So it's sort of understood. So VD pi P is P, right? So this we saw last time by basically taking the permutation inside here and then updating the summation index, right? So this was fine. Second thing we showed was that P symmetric square is P. Okay, let's not write symmetric. P square is P. Okay, so this I'm calling P. It's a notation. To see P square is P, we just use this property, right? So you write it out and apply. So you expand one of these P's as here, right? And then you see that VD will act on P, but it will give you P, and so you could get it. And then now we look at the fact that it's self-adjoint. This is self-adjoint, right? Okay, so why is that? Because, so let's work it out. So P dagger would be 1 by k factorial sum over pi VD dagger pi, right? This is sum over all permutations. This in turn is going to be equal to 1 by k factorial, and we know dagger is going to make it inverse, so you'll have pi sk VD pi inverse, right? And this is basically just a change of variables because you're summing over all permutations, so you can do that. Okay, which is P, right? So there's nothing very fancy here either. Okay.
Because it is a representation. V dagger is V inverse, but V inverse pi is V pi inverse.
Say it again.
So V dagger is V inverse.
V dagger is V inverse. Yeah, it's a unitary.
You use that V inverse pi is V pi inverse.
Yeah, I mean this property we directly already proved earlier, but yeah, you can expand it if you want. Right. Okay, good. And then, so what is the conclusion? The conclusion is that that P is an orthogonal projector, right? So basically it's a matrix, with its Hermitian, you can diagonalize it. It's not Hermitian, is it? It is Hermitian actually, yeah. So you can diagonalize it and it'll have 0, 1 eigenvalues, right? And so it's basically, so the remaining space is orthogonal, so it's sort of fine. Okay, and then, so now the strategy for the remaining part of the theorem. Oh, I didn't write the full statement, is it? And the statement also said that, okay, I didn't write the full statement, it seems. But okay, so there's also the fact that image of P symmetric is the same as, this actually matches. So to show that, the strategy is that we show the image of P is contained in the symmetric subspace CT, and then the second one is symmetric subspace CD is contained in image. Okay. It turns out that, yeah. Okay, let's just continue. Okay. Okay, so proof of 1 is, so you note, so here's another one, which is P acting on psi is going to be contained in the symmetric subspace CD for all psi. And this is basically just because, so VD pi, so you take any permutation, you apply it on P psi. This is going to give you, because VD acting on P is P, right, from NB1, so you'll just get P psi, right? So and this whole thing is therefore inside the symmetric thing, right, because this is true for all. So for all pi, this is true. Yeah. So that's why this is true. The next statement we want to show is that the symmetric subspace is in the image, right? That's also easy to check. So you take any psi which is in the symmetric subspace, right? And then you apply P symmetric, or just P because I'm just writing P. You get 1 by k factorial, sum over the permutation, VD pi acting on psi. And we know because it's symmetric, right, this object is also going to be psi, right? It doesn't matter how you permute it. So you're going to get 1 by k factorial, which is pi sk psi. And this thing is just normalization. These are numbers. You'll get 1. Okay. So that gives you the last property. Okay. So that concludes the proof of the theorem. Let's move on to the dimension argument. So all of this is, yeah, okay. I'm hesitating to say this, but the thing is that I don't think we actually need all this later. But since you started it, let's finish it to the extent that we initially set out to look at this. But maybe it's needed in the oracle separation result. So let's see. Okay, so dimension of the symmetric subspace. Okay, so we want to argue that trace of P symmetric decay is going to be the dimension of this symmetric subspace C to the T. Okay, and the claim is this is k plus d minus 1, choose k. When I do the calculation, I get a k minus 1 here, so I'll show you what I'm doing and then you can tell me what I'm doing wrong because I'm missing something and I can't quite see what I'm doing wrong. Okay. So what is this saying? It is saying that you take the projector for the symmetric subspace, take the trace, and the number you get is going to be the same as the dimension of the symmetric subspace. So we can do the calculation. I don't see intuitively why this is the case, but here's the formal proof. Okay, so the first equality holds. Okay, so the first equality holds because P symmetric, dk is an orthogonal projector onto symmetric CD. Right, so it was basically just the statement I had written earlier, right? Like you'll have 0, 0, whatever, and then you'll have 1, 1, right? There is a basis in which this is the case, and then you trace it, and you get the dimension of the space. So that part is sort of straightforward. Okay, and then second part is that the symmetric space CD is the same as image of P symmetric, right? This we showed over here, right? So what that means is that it's basically the span of P symmetric acting on I1 to Ik, where I1 to Ik are each of dimension d, right? Okay, so we've not really done anything. You had a basis, and then you're just projecting and taking the span. So they should give you essentially everything you could have in the space. Okay, and now our goal is going to be that we count the number of independent vectors in this set. Okay, so there's a bit of a counting argument, so it gets a little bit delicate, but let's see. Okay, so suppose that I1 to Ik and J1 to Jk are such that I1 to Ik and J1 to Jk have the same number n sub m of elements equal to m, okay, for all m in T. Okay, so what you do is, so for example, if m is, say for example, m is say 5, okay, and this is, these are taking, and say d is like 10, okay, so d is 10. So each of these indices is going to be from 1 to 10, right? I1 is going to 1 to I2 is going to 1 to 10. So you're just counting how many among them are equal to 5. Okay, that would be n sub 5, and then how many are equal to 6, n sub 6, and so on. So that's the notation. Okay. Okay, and where was I? Okay, good. And note that there exists a unitary operator Vd pi such that Vd pi takes I1 Ik to J1 Jk. Okay, because the number of ones, number of twos, they're all the same, right? So you can move them around. You're following, right? So, for example, this could be like 1 1 5 5. This could be 5 1 5 1. Number of 5s is 2. Number of 5s is 2. Number of 1s is 2. Number of 1s is 2. So it's just checking this, right? And once that is true, you can permute it, and that should be fine. So that's sort of elementary. Okay. The second NB is that because PDK symmetric, which I'll probably stop writing in between, VD pi equals PDK symmetric, right? This we just saw. It follows that P symmetric acting on I1 to Ik is the same as P symmetric acting on J1 to Jk, right? It's sort of fine because permutations make no difference, right, to the action of P symmetric. Okay, good. So now, so we therefore define vectors using this notation. So n1 to nd, okay, and each of these is saying how many elements there are. Sorry, how many indices correspond to, like how many systems have the value 1, how many systems have the value 2, and so on. Okay, and there are how many systems at most k. So each number can be at most k, right? And they have to sum to k, of course, such that n1 plus nd equals k. Okay. This is fine, right? The notation is clear. If you get lost, tell me, okay? Because it's a bit confusing. All right. So now here's a definition. So for n1 to nd in k, okay, with that constraint, with n1 plus nd being at most, being exactly k, we define the following. So n1 to nd is defined to be PDK symmetric acting on I1 tensor all the way to Ik. Okay, maybe because we're sort of overloading the notation, maybe we can just put tensors here as well. Because normally we write tensors also as a single string, but now they want to use the single string to represent this specific state. Okay. And what is the constraint on these guys? The constraint is that it has to satisfy this, right? So it's any vector. This is any vector such that for all m in D, there exists n m distinct systems subsystems J such that I sub j is m. Okay, all this is saying is that, you know, this vector actually has, you know, so if it says there are two ones, then it actually has two ones. It's 2 5s, it actually has 2 5s. That's all it's saying. Okay, and it doesn't matter obviously which one you choose because of this property, right? Because regardless of which one you pick, it's going to become the same once you apply the operator. Okay. Okay, and now we note that these vectors are orthogonal and hence linearly independent. Okay, why is that?
Right hand side will be so
Right, there has to exist. I mean, if the numbers don't match, right? Like if there's, suppose this one has a 6, right? Then obviously it's not going to be, like there'll be at least one element which would, product to 0, like you said, right? And okay, I hope that's clear. Okay, and if they're orthogonal, they're linearly independent. So that's done.
I don't understand why did you write P there
Where? Here?
in the definition of N1 to ND?
Because you're looking at the symmetric. Otherwise, it would depend on the sequence, right? Like then 115, for example, would be different from 151 and so on.
So what is this ordering now? So if you put P
It
there,
makes it into a symmetric subspace. It makes it into a superposition, right? That's what the projector P is doing, right? Remember, the projector P is just a superposition over all permutations, by definition.
oh, okay.
So it doesn't matter which order you pick; it will automatically produce a superposition over all orders.
Yes.
Does that answer your question? Or maybe I didn't understand your question. What was your question?
So N1 to ND is symmetrized vector.
Yeah. Exactly. So you're just asking how many of each, and that's enough because the order doesn't matter. Almost like bosons, right? Like you're just looking at the number of. Okay. So this is fine. The second note is that the dimension of the symmetric subspace, right, is thus the number of linearly independent vectors among N1 to ND, right, where the sum is K, right? Okay, and so basically what you're choosing is that so you can think of this as having so you have, say, K objects. Yeah, maybe the best way to do it is using let's do it using the star and, what is it called, the star and dash? No,
I forgot the name. Yeah, that is very.
star and bar. Okay, yeah, probably star and bar. If it's not, we'll see what it is. Okay, so the star and bar argument is the following, right? That so we have a total of K objects, right? So you have K stars, and you want to put them into different buckets which are labeled. So you have D buckets. So I'm going to put a bar. It can be like in different locations. So these two are fixed, right? Because you can't leave objects. The sum has to be K, and then this one's going to be the first bucket. This is the second bucket, and so on, right? So now really the question is, in how many ways can you put these dashes in this sort of a picture? And the stars are identical, right? Because they're just numbers that sum to, right? Is that okay? So what you basically need to do is, so for example, let's just take a very, very concrete example, right? So here you have 1, 2, 3, 4 buckets, but you have 1, 2, 3, 4, 5 bars, right? So you need to pick D minus 1, okay? So you have to pick D minus 1 locations. In this case, D minus 1 would be 3, right? D, the number of buckets is 4. You have to pick D minus 1, which is 3, right? 1, 2, 3. You have to pick 3 bars. Everything else is fixed. And how many locations do we have? Because anywhere you don't pick is going to be a star, right? So how many locations do we have? Yeah, how many? I heard you.
Why can't a bucket have zero?
It can, right? Why not? You just put it like this. Right, so you can have 0. Okay, so basically how many, so you have to just count the number of stars and the number of bars excluding the last two, because those are not allowed, right? So those are all the positions where you could potentially put a bar, right? Yeah, right? So how many locations do I have where I can put a bar?
Number of stars minus 1.
So n plus D minus 1, right? Okay, and then how many do I have to choose? Right. So that's why I'm getting D minus. Oh shoot, did I screw up the D and K? Oh, the number of buckets was K. Sorry. Wait, did I mess up entirely? Uh-oh. Wait. I think so the total n is supposed to be K, because the total number is this. Okay, so at least to get this correct. Right. And
Yeah, that's the same.
huh?
Those are the same.
Those are the same? Okay, good. So I didn't do anything wrong. I was just missing some algebra as usual. Good. Okay, so good. So everything checks out. Sorry. Okay, so that's the argument for how many linearly independent vectors you're going to have, because that's the number of independent ways you can bucket K things. Okay? Good. Yeah, okay, I now remember. You just have to write down the expression. It's identical. Okay, good. Yeah, no, in my notes I had written K minus 1. I think that's why I was getting confused. So I just ran the argument wrong. That's why it was happening. Okay, so so we now look at the antisymmetric subspace. Okay, so I was going to do the antisymmetric subspace, but let's skip that. So I'll just give you the theorems, and the proofs I'll leave for the assignments. Okay, there's essentially analogous there in the paper, so you can look them up. So the antisymmetric case is analogous. The counting, of course, is a little bit different, right? Because they're fermions, so things will cancel and so on. Okay, so what is the definition of the antisymmetric subspace? Okay, so it's the following set. So A sim sub K CD is defined to be psi in CD tensor K VD pi acting on psi. Okay. Any guesses? For the symmetric case, it was just psi, right? So something has to change here. What do you think would change?
Minus.
Come on, you should know. Uttam bhai. Minus sign? No. It's a sign, but it's not a minus sign necessarily, right?
Antisymmetry, right? So it will pick a minus sign.
It will depend on the number of odd cycles, right, in the permutation. Right. So it's the number of, it's just the sign of the permutation basically. Okay. No, I was saying this because I thought we saw this last time, and you were the one who told me that I don't know, for sign of identity is or odd, the sign of like I think it was that if pi is odd, then sign of pi inverse is also odd, and because it has to give anyway. Let's not get there. We'll do it when we have to, but that's the thing. Okay.
Yeah, if there are only two systems, then
Exactly. Yeah. No, that also assuming that you're not applying identity permutation.
Yes.
So even there, it actually happens.
Yeah, but I remember if you exchange, then you can pick a minus sign.
Yeah, which is exactly the same thing. Yeah, precisely. Which is what Shreyas was also saying. Okay. So where this thing is the sign of the permutation, because I'm not writing it. So you understand. Okay, good. Okay, so story. Okay, so again, we'll define the corresponding projector, right? So P asymmetric. This is D comma K. Right? So the definition is notation P asymmetric dk is 1 by k factorial. Okay, now what should be the definition? There's VD pi. So we have to add something here. Yeah. Sorry, I'm just being silly now. Of course. Okay. And the theorem is the following. So the operator P asymmetric dk is the orthogonal projector onto the antisymmetric subspace, right? So onto antisymmetric K on CD. Okay, so this proof I will, let's see if I run out of things to explain today, then we can come back and complete this proof. But let's see if I can actually go on to the, yeah, maybe I will have time later. Let's see. And then the proposition, right, so doing this orthogonal projector business basically allows us to say that the dimension of this and this are going to be the same, and then we'll compute the dimension of this object just like we did in the previous case. So here there's a dependence on D, right, because it's like fermions. If you don't have enough space, it's going to vanish. So if D is greater than K, so if you have so D is the number of copies, right, and K is denoting how many particles intuitively, right. So if you have enough space and fewer particles, then the state will survive.
K was the number of copies.
Yeah. So K is the total number of particles in a sense, right, because it's symmetrizing or anti-symmetrizing overall. Okay, so PDK antisymmetric is going to be dimension of symmetric KCD. Okay. Any guesses? I would not be able to guess if I had to guess on what the analogous operation of expression of this should be. It's much simpler actually. Actually, in a sense, it's yeah, because I think you just have like lots of spaces, right? You have all of these spaces, and you just have to pick D of them. Yeah, it turns out to be this. So you're choosing, you have D options, and you're choosing K to place the particle, because if you put two particles in one, it'll disappear, right? So intuitively, I mean, you have to do the calculation, but Okay, so this D choose K, and if you don't have enough space, then it's just going to vanish. Okay. So, okay, we'll see if we can come back to the proof. Okay, so now let's do something more interesting. Let's see how these two talk to each other. They're sort of cute. Okay, so proposition 21.
I cannot have two same numbers in this I1, I2 notation. Otherwise, antisymmetric thing will kill it. So each number has to be unique. Appear at once.
Yeah. So you can only have 0 or 1 basically, otherwise it goes. Yeah. Louder? Yeah. Well, you can show that it has to be either 0 or 1, but I don't have enough intuition.
No, for example, if there is 3, then you will find one permutation that will kill it.
Yeah. Yeah. Okay. Right, because if you have like 1, 1, say 2, right, then you can flip these and it'll pick a minus sign and it would vanish. Or if you have.
Even if you have 3, then you can have.
Yeah, if you have 3, then the argument is already true anyway, right? Because you flip any 2, it'll disappear. So you really have to have everything unique, 1, 2, 3, and so on, so that permuting nothing. Okay. Yeah, thank you for that. I hadn't considered it carefully. Right, so here's a nice fun one which says that if you have asymmetric decay dagger and you have symmetric decay, then this is going to be 0. Okay, and in particular this means that P decay, asymmetric, and P symmetric decay are orthogonal in the Hilbert-Schmidt norm. Sorry, Hilbert-Schmidt in a product. Okay.
It's also permutation, right? Is the same kind of argument?
Yeah. It is self-adjoint. Yeah, it is the same thing goes. Yeah. Yeah, I think they're writing it so that it's in the form of the Hilbert-Schmidt in a product explicitly. So when you take trace, yeah, that's fine. Yeah.
This is much stronger statement than trace.
This is much stronger, yeah. Yeah. I mean, I don't have a proof that it's strictly stronger, but a priori looks stronger for sure. Okay, so we first do the thing that Uttam Bhai said, right? We're going to assume that it's asymmetric. Oh, sorry, it's self-adjoint. And then we just open it up. So pi sk sine of pi vd pi, right? That's just the definition of the asymmetric projector. Multiply it with p symmetric, right? And this we know doesn't change anything, so this would give us the same p symmetric. And this part we claim is going to be 0. Okay, because this is constant then, the sum will vanish. Right, this we already proved that a permutation acting on the set of all permutations, the sum of all permutations will vanish. And so how do you prove that little claim? So proof of claim is that 1 by k factorial sum over pi in sk sine of pi is 1 by k factorial sum over pi sk sine of tau pi because you're summing over all, right? It's just a change in the summation index, so we've not done much. We just added some explicit tau, and this is going to be the same as the sine of tau, right? Because sine of 8 times b would be sine of 8 times 8 sine of b, right? So you get the remaining thing back. Sk sine of pi, and then this object is going to be minus 1 by k factorial sum over minus, because you can choose a tau such that the sign is minus, right? And then it's the same object as what we started with, so then this has to vanish. Okay, so that's the that shows these things are orthogonal. Okay, so far so good. Right, and now it's okay. For k equals 2 and d greater than 1, dimension of the symmetric group for 2 elements, with 2 systems, the asymmetric with 2 systems. Okay, this dimension is going to be what? D plus 1, 2 plus d choose 2, and this turns out to be d square. Okay. So why is this relevant? It's relevant because it basically means that so you can basically write it as a sum of antisymmetric and symmetric and antisymmetric, a direct sum. Right, because we already established that these two things are orthogonal because the projectors are orthogonal, right, and they corresponded to the respective spaces, so they are and they also span, right, because the dimensions add up. So that's the okay. Now that we're doing it, might as well actually also write. So now because PD2 symmetric and P asymmetric D2, right, are both linear combinations of permutations, it implies they commute with U tensor 2, right? Because it doesn't matter what order you're in for all U, right? So basically that means that these objects are in the commutant, right? That was the definition. Okay. So they are elements of a basis. They're also orthogonal, right, from NB1. So they're elements of a basis for the commutant UD k equals 2. Okay. Orthogonal, and the dimensions match. So basically all it's saying is that you can you can just use it as a basis for the commutant for the case where you have only 2 systems.
So why was the first case taken so that the combination of permutation
Oh, because in fact it's not just true for unitaries, right? Any operator that which is identically acting on the subsystems, it doesn't matter whether you permute them, right? So it will commute. Permutations are just swapping systems, and if your systems are identical, which are identical in the sense the operator is identically acting on the systems, it will commute, right?
It will commute with what?
Oh, it being okay. So basically, all I'm saying is VD pi. So if you're on k dimensions, right, u tensor k, this is going to be 0, right?
VD pi commutes.
And this is just a linear combination of VD pi's, right? Right? Maybe I'm misunderstanding your question.
No, I was asking.
Okay. Okay, so then, so one can use this basis to find, the commutant for the second moment and so on. So we're not going to, we're going to skip a few more things, which I will also leave as an assignment, and come back to it if you have time. But for now, I wanted to focus on this theorem, which is why I started doing all of this in the first place. And it turns out that we don't need all that machinery as much, except for the normalization to do the theorem. So the theorem statement is the following. Theorem 22. Let d comma k in be natural numbers. Then for all phi in CD, yeah, maybe actually I should say one small thing before continuing. So okay, so the consequence of this is basically that if you want to compute, say for example, the commutant of some operator here, so u tensor 2, with two systems, right? Right. So if you want to compute this object, you can use all these results to write it basically as follows. So you can write the symmetric projector, normalization of the symmetric projector. With the operator O, take the Hilbert-Schmidt norm, okay, take the symmetric projector. Let me just write the hat, okay. So symmetric hat basically means this is normalized, okay. So you can take the inner product of the observable with your symmetric subspace, write the symmetric subspace, plus you can write the asymmetric projector, not subspace, sorry, projector, Hilbert-Schmidt norm, multiplied by p hat asymmetric. So that's why all the machinery was sort of introduced, that if you need to compute something in these two dimensions, with two systems on higher dimensions, you can use the symmetric and antisymmetric projectors to compute the coefficients. Okay. So that sort of ties all these results together.
How are you doing this thing?
Oh, because it's they are orthogonal in the Hilbert-Schmidt norm, right? And they have the same, like the correct dimension. So you can write any operator in this as a linear combination. Yeah. Oh, I was just writing it from the completeness that. Yeah, I was just thinking of it as, the usual matrix algebra or whatever we do, right, with vectors, with vector spaces. So if you have a basis that spans the space, then you can just take in a product and find components.
So this thing is average, right?
This thing is?
Left hand side is Haar average.
Oh, that is just a statement that, it doesn't have to be this. It's any object in the commutant, doesn't matter. This is just a special case that it happens to be in the commutant, and then you're using the fact that this will commute, right? U tensor 2 will commute with the. When you take the trace, it won't make a difference.
So this is commutant of O, then commutant of O you can write like P is in symmetric plus
Yeah, you can put this UU dagger if you want, but they'll disappear. It doesn't matter because it'll be in the inner product, and then P symmetric commutes with U tensor 2, so it won't play a role. Yeah, is that okay? Okay, so in what I'm going to describe later, I don't think we'll use that property directly per se, but maybe in the oracle separation, like I was saying, maybe these things would be useful.
Basically, if you have higher order like moments, then you just need to find a basis for commitment, and then
Higher order moments, then the symmetric asymmetric stuff won't work because
yeah, you just need to find basis for commitment.
then you have to do it more generically.
Yeah, here this was basis
And
for the commutant.
yeah.
So the commutant will have more elements as we increase the number of systems.
So we know that it's going to be spanned by the Shu-Weil duality. We know it's going to be spanned by the permutations. It'll be a linear combination of the permutations, this commutant.
Yeah, there will be.
But yeah, finding the coefficients is not so straightforward because things are not orthonormal in general, right? So that's why in particular using the symmetric asymmetric projectors are nice because they're orthogonal, so that makes things easier to compute.
No, if I find the basis for the commutant, it will.
Yeah, of course. That's what it's doing. It's doing it in a special case. It's finding the basis, exactly.
Just that I will have more subspaces than P-symmetric and P-symmetric.
Right. Okay. All right. So let's get back to the theorem. So D and K are natural numbers. Phi is some CD. Okay, and the moment operator is a uniform. Okay, that's the new thing that we're able to show here. It's a uniform linear combination of permutations. Okay, what does that mean? It means you take the moment operator. So this, remember, was the definition of the moment operator, right? So if you have some observable, you take U from the Haar measure, and you apply k copies of the unitary on this object. Dagger. Ooh. It's actually not taking. It's okay. It's taking O to be phi rank 1. So I guess that's somehow important. Symmetric decay divided by trace of P symmetric decay. So P symmetric decay is just the sum of all permutations, right? So basically the coefficients are all 1. We knew already that it is spanned by the combination of permutations by Shu-Weil duality. This is saying that the coefficients are equal. That's what remains to be shown. Okay, so here pi symmetric decay is 1 by k factorial pi in sk vd pi, okay, and trace. So that's why we did all the hard work of doing the permutations and me getting confused with the two formulae of star and bar. So the dimension of so this we already proved, right? Because the images were the same. Because the subspaces are identical, and image of the projector and this subspace is identical, and then this we computed to be k plus d minus 1 k. Right? So that's why we did all the hard work. So we actually knew the normalization. And the remaining argument is actually extremely straightforward. So let's quickly do that as well.
Because phi is symmetric for you, so this inner product will go to the other inner product. In the expression where you write P symmetric plus P adjacent.
No, this is for the general case.
Oh,
Okay, so first we recall that this is show while duality, right, which says that you can have so this can always be expressed as a linear combination of permutations. Right, and our strategy is now going to be to multiply or left multiply with VD sigma inverse and simplify. Okay, where sigma is some permutation. So let's see what that gives us. So first observe that VD sigma inverse mk. So I'll just write m sub k, okay, for this object. Okay, so m sub k phi tensor k is sub k phi tensor k, right? Why is that? Because VD sigma inverse commutes with u tensor k for all u, right? So this part is sort of straightforward because the argument that I just gave, right, that they're all the same u's, so permuting them will not make any difference. I also had it written somewhere. This argument right here. So it's just saying that. And second is that VD acting on sigma inverse phi tensor k is also going to be the same as phi tensor k, right? Essentially the same idea, right? Instead of an operator, you have a state. As long as they're identical, permutations are not going to make any difference. So you use these two facts in just the definition. So this would allow you to go past the unitary, and then the O itself has this special form, it's phi tensor k, so that will also be unchanged, right? So you essentially get this statement. Is that okay? Yeah? Tell me, okay, if something's not clear. And the second note is the following. So this was us analyzing the left hand side, okay? So this thing is m, right? M sub k of O, right? So we analyze the left hand side. Now this is the right hand side, I think. So now what we're going to do is we're going to write down the right hand side with this multiplication of sigma inverse, and this is going to become the following. There's pi sk and then c pi vd sigma inverse pi, right? That's just because of how the permutation representation was defined. And then this is a change of index, so this would become the same as c sigma pi. So that's why we used sigma inverse here, so you get a sigma pi here, right? We didn't have to, but doesn't matter. Okay, so when you combine these, we're almost there, right? I think the argument is almost clear now. Okay, so now when you combine these, so combine all to get that m sub k acting on phi tensor k is the same as pi sk c sigma pi vd pi, and this statement is true for all sigma, right? All permutations sigma. Correct? That's what we sort of showed over there, because sigma was arbitrary. Okay, and so now we're almost there, right? For d strictly greater than 1, okay, so the permutation actually makes some sense. In that case, we have that this thing implies C sigma is just the same as the first entry, okay, for all sigma. Okay, so this is relatively easy to see, because all the VD pi's are different, right? They're different permutations. So you can choose to swap any two elements that you want to show are the same, take the difference, because it's identical, and you'll only have those two terms, the difference of those two terms. So you'll have C sigma minus C identity from the first term, and then C identity minus C sigma, and then you'll have to, and then the difference of the operators, which has to vanish. So you'll get that these objects are the same. You can work it out. It's not very hard. Okay. Do you want me to do it, or?
I can follow.
So basically, it's saying that intuitively, it's saying that you have some you have, say, you have V1 pi. Oh, sorry. Let's fix VD. Okay, so you have say identity, right, and then you have flip, right, and then it's saying if this was AB, this is also the same as BA with the same, right. That's what it's saying, really, right, because you can permute it with whichever way you want. So then it has to be the case, as long as these things are distinct, right, it has to be the case that the coefficients must be the same, otherwise the two objects cannot be the same. You can just take the difference. Okay, so you'll get A minus B times something is the same as plus B minus A times something is 0, and these two things are different, so they both have to be 0, otherwise you cannot make them vanish, right? So you can repeat the argument in general, so that would give you the final thing. And then, okay, so the final note is that so mk phi tensor k is going to be the same as right. You can pull out the coefficient, right, because it's identical in all cases, and this basically gives you exactly the expression we wanted, right. So it's given in terms of the symmetric projector, because the definition of the symmetric projector was just the sum over all 1 we given. These two? Oh, because these things are distinct, right? So if the whole thing has to disappear, this? Oh, because of this fact, right? It's true for all permutations. So if I permute systems 1 and 2, right? I'm allowed to permute the coefficients, right? Independently of the VD pi. Sigma is arbitrary. Sorry, which? Here? Yeah, but this is true for all sigma. Whichever permutations you take, it will always be, this statement is always true. So I'm just taking a special case of this. Oh, this statement?
Yeah.
Uh-huh.
So to say A times bi plus B times VD
Uh-huh.
plus B times VD pi.
Uh-huh.
Sorry, VD flip is equal to B times VD identity plus A times VD flip.
Uh-huh.
We are picking a certain sigma, right?
Yes.
So what does it mean that for all sigma belongs to SK this holds like C sigma equals C?
That is any constant. So just like we did, like in the previous case, previous class, that we showed that some coefficients are equal, so we choose certain permutation and we can make every coefficient equal.
I mean, this is just saying this, right? Like you could write pi if you want. You could write, flip pi if you want. Like you swap 1 and 2 systems, say for example, this is the permutations.
this was just example. So since sigma is arbitrary, you can have as many equations like this as you want. As to the
All
next
the other
step.
things you keep same, right? Suppose you're arguing that these two coefficients are different in a huge thing. I can say I'll just permute those two, take the difference, everything will vanish, and those are the right. So I actually didn't understand what the question was. Maybe you can tell me afterwards.
Slightly confused because of the for all sigma belongs to SK in the note, like NB4.
Yeah, so this equation is true for all sigma. So this same object.
And the one after that equation is fine. Like,
Oh, did I screw up here? Oh, I see. So NB4 was the issue. Yeah, okay. So what's the problem? This is just saying all coefficients are the same as the first one.
yeah. So I wasn't getting it fully, but now I do get it. Like,
Okay.
yeah.
Sorry, yeah.
First or last, it doesn't matter. I mean, they are equal.
Yeah, exactly. Yeah, this is just convention. You can pick any. Okay, so the argument is fine. So that basically completes the proof. That's and it was basically because of this statement that I went into this rabbit hole, because Andrea had just claimed that this is true and it looked very mysterious, and I thought that it would be used in some way. So at least in what I'll describe now, it's not being used in any non-trivial way yet, but I'll find out. Okay, good. So now we're going to start with. Ooh, we have some time. Very nice. Okay. So now let's start with building commitments from pseudorandom state generators. So let's start from here. So I'm going to give you the the rough definition, and then I'll give you the intuition behind the construction. It's very cute, and then we'll try to formalize the requirements, and next time we'll do the formal proof. Okay. So, okay, sorry. So this is a paper by Morime and Yamakawa. They're both monsters in the field, or giants in the field, which is the most standard usage. So we're not going to do signatures, okay? I'm just writing the title of the paper. Okay, so quantum commitments. So we'll be committing classical messages, but using quantum things. And the nice thing is that we'll do it without using one-way functions. Okay, and classically we don't know whether it's possible to do it without using one-way functions. And there's like strong formal evidence that it is indeed impossible. Tomo Yuki Morime. So I was trying to invite him for a talk for one of the papers, and I think one of the co-authors is going to present it. Hopefully, we'll see if we get confirmation. Okay, so
What was the year of this?
I don't know, maybe 2022, something like that. Sorry, I will. Yeah, you just search the title, it'll show up. I'm sorry, I should know, but actually I have the paper. (2022). Okay, introduction. We're going to start right from the background, okay? Because we already do a fairly long introduction right in the beginning, so you're kind of motivated with. You are it. Okay, I'm assuming you're motivated. So we're going to assume that. No, but really, the motivation is just that we're trying to use primitives that are weaker than the weakest primitive in the classical setting, right? So we're trying to see, and there's like lots of formal evidence that is given. So we'll look at one of these formal evidence for why what we're using is weaker than a one-way function. But today we're going to look at how to construct, using that primitive, these commitments, which are not known classically. Okay, sorry, not known using such weak assumptions classically. Okay, so assume that a sender wants to commit. So this is just introducing commitments a little bit more carefully. Well, sorry, intuitively, and then we'll do it formally. So they want to commit to sending a message M later. Okay, so what they do is so the sender encrypts M, so encrypts in quotes, okay, M, and sends it, okay, and then later, so it's like a two-phase protocol. So there's the first phase where you encrypt and send, and then there's a later phase where you're going to reveal it. So later the sender sends a key. Sender sends a key to open the message, open the encryption if you like, encryption and reveal. Okay. Okay, so the properties we want, right, this we already saw earlier. So the first property is that before the sender sends the key, the receiver should not learn anything about the message, right? Receiver shouldn't learn anything about the message. Right? So that's reasonable. And the second property is that the sender should not be able to change the message. Once it has committed. Right? Those are the two basic properties. Well, classically, yes. Yes. But I think requires a one-way function would be when you're trying to do it with, like for example, it could be using a one-time pad like for 1 bit. Right? One-time pad doesn't require a one-way function. It's only when you're trying to compress things that you sort of start needing one-way functions. So even then it's not really. Yeah. Okay.
What was the question I was asking?
No, I think he was probably using the result I asked him to prove in the assignment, which was that if you have symmetric key encryption, but with like a longer length, then you need a one-way function. So he was saying that already at the encrypt stage, wouldn't you need a one-way function, which is not necessarily the case depending on the length of the key. So my response earlier was incorrect. I said for classical, but no, it's even true quantumly. Oh, sorry, it doesn't depend on classical or quantum. I think you can construct encryption without having to assume one-way functions as long as the key is big enough. Okay. Sorry about the aside. Okay, so the properties are fine, right? And so informally, what is known is that both quantumly and classically, both binding and hiding cannot be satisfied statistically. Okay. This was one of the assignment questions, right? So you guys already know this. And statistically basically means that you're not assuming that the adversary is bounded.
First one is hiding, right?
Yeah, hiding and binding. Oh yeah, my hiding and binding almost look the same. Shoot, I'm sorry, you guys. I'm just trying to write a little faster than I normally would. Okay.
The property one is hiding, right?
Property one is hiding, yeah, because Alice should not learn, or sorry, the receiver should not learn the message. So the message is being hidden, and binding is that the prover, the sender should not be able to change his mind or their mind to be more inclusive. Okay, so question, what is the, yeah, okay, so this is what's known, okay, and then the question is, so this is basically saying that you do need to make some assumption. You cannot hope to do it without making any assumptions. And the question is, what is the weakest assumption to build this object? What is the weakest assumption? To build commitments. Okay, so that was the very informal part of the thing. Now this is like the semi-formal part, which is the tech overview. And this one is going to be way simpler than the tech overviews we've seen in the past. So yeah, such results are hard to come by, right? That are both important and simple to state and prove. Okay, so commitments. So the story is the following. Okay, so the basic idea is generalization in some sense. Generalization of the classical what is called Naur's commitment scheme. Okay, so it's a classical commitment scheme which I'll describe in just a moment. So let's recall it. Okay. Okay. So this is recall that scheme. Okay. So it uses a PRG, a pseudo-random generator, which takes 0, 1. So it basically expands an n-bit string into a 3 n-bit string. Okay. Yeah, this is like the usual stuff, right? Like we did in encryption. Like you shouldn't, the message you get should essentially be, like from the cipher text, it shouldn't be clear whether, say it corresponded to M0 or M1. The distributions should be identical. Yeah, it's the same sense, yeah. Okay, so here G is a PRG. A PRG is a pseudo-random generator. Basically, it's going to take an n-bit seed. So you give it a uniformly random input, and the output it produces is going to be indistinguishable from random for somebody who doesn't know the seed and is computationally bounded. Okay. So here's the construction. And the construction is very cute. Maybe let me write it on the other side since it's going to be nice. Oh man. Okay, so sender, receiver. Okay, so the receiver first sends a message. Okay, so the receiver sends a 3 n-bit string eta to the sender. Okay, the sender samples a seed of n bits. Okay, this is the commit phase. Oh my god, looks horrible. Okay, and sends GS O plus eta to the B. Okay, eta to the B basically just means if B is 0, you don't XOR. If B is 1, you XOR. Right? That's the.
So sender to this B.
Yeah, the sender is the one who wants to send the message B, right? Yeah, the message M became B. Sorry, it became a bit from being a message. Yeah, let's just say it's B. Thank you for pointing that out. Okay, and then this is what we're calling commitment. So let's call it CMT. And so okay, so that's the commit phase. Okay, so it's done. And now when he has to reveal or open, what the sender is going to do is it's going to send B comma S, which is open. Okay. So basically sending the seed and the message that was sent, and the receiver is going to accept B if CMT equals GS O plus eta to the B. Right. So she's just going to check that if she plugs in the seed into the pseudo-random generator and she XORs it with, eta if the message was 1 or doesn't XOR it, and she checks if the thing actually matches. Okay.
Message being given is B.
Yes.
And then we send it.
And then we send it. Yeah, in the opening you send the message. Yes, because you want to. So basically the key thing is you want to make sure that it's hidden in this phase, and you also want to make sure that the sender cannot change their mind in the open phase. Right. Okay.
If they send like not B, then it won't decode it as eta.
If they send not B, it will not decode. Yeah, we'll do the analysis. You can already start thinking about it. Yeah, think about how you would do the analysis. That's a good point, right? So suppose you sent the encryption for B, how would you send a successful opening for not B, right? That's what you're asking. Okay, so first let me ask a simpler question, right? So let's start with hiding. Okay, so for hiding, do you think hiding is statistical or computational? So hiding is, remember that the receiver should not be able to learn the message B. Right. Right. Okay, so the message is, so we're going to have to use the fact that this GS looks random, right? Otherwise, and you can only use it if it's if you assume that the receiver is bounded. Okay. So this is sort of clear, right? So the receiver cannot distinguish G of S from G of S XOR eta, right? Because they're both identically distributed as far as a computationally bounded adversary is concerned, correct? So that part is simple. So this is computational. Okay, and binding, this is going to be statistical. Okay, so if both 0 and 1 can be opened, okay, then there exists S0, S1 such that G of S0 is G of S1, oh sorry, XOR is eta. Okay, because say the prover sent GS, right? If he wants to open to 1, he would have to be able to find GS prime. Let's send S prime. He'll have to find GS prime such that GS prime XOR GS. Sorry. Looks like this thing XORed with eta, right? If he wants to send a 1 instead of. So if it's a 0, it just sends S. To send a 1, he'll have to send an S prime such that this is true, which is just saying that, you know, this statement, right? So it has to be able to find these S and S prime.
So in the case that eta is sampled to be just zeros,
Yeah.
then won't the acceptance happen regardless of the bit being 0 or 1?
Yeah, but this is, remember the question on whether security holds if a specific string is the case. Like that's the hello question, right? I had given. Like if the one-time pad was all zeros and your message was hello, then you could say that, oh, you're XORing hello with all zeros, I can read the message. But you have to think in terms of distributions.
Right.
That all messages are equally likely. So purely by chance you will get hello, which is correct. It should happen. Right? So
But doesn't this violate the binding being statistical? Because
oh, maybe I'm missing something. Okay, say again. Maybe I misunderstood your question.
so binding being statistical means under any adversary this okay, I will only accept the correct bit, right?
Right.
So if for some case probabilistically I could get eta to be just zeros, in which case I would accept B regardless. I would accept whatever bit the sender sends to me.
Right. No, that is a good point. So there's the distinction we want to make here is perfect versus statistical. So the argument I'm going to give is going to be with negligible probability. It is statistical, but it will succeed with negligible probability. That's a good point. Thank you. Sorry, I misunderstood what you were saying. Okay. So, hi. We're okay. So let me just quickly say that. So there are okay. So here's the counting argument. So there exist at most 2 to the 2n such S's, such choices. Okay, each is n bits, so that at most 2 to the sorry, let me just write it. I'll explain it more next time. Okay, so the argument very quickly is that there are at most 2 to the 2n choices, and eta is sampled from 2 to the so that 2 to the 3n eta, right? But there are 2 to the 3n etas. Okay. So the probability that you would get one of the good etas is going to be probability of such S's existing is at most 2 to the 2n divided by 2 to the 3n, which is 1 by 2 to the n. Right, because there's only a small, like even if you look at the span of S0, S1 over all possible choices, right, in this big eta space, right, so G's, this is the space of S's, right, the space of S's is small, the range is huge, so the maximum number of etas you would be able to span is these, right, even by choosing, but the probability that those will be chosen is very small. Okay, so that's why your example is true, because in some cases you would be able to do it. Okay, so let's stop there. We will do the quantum construction next time.